Some migratory birds cross oceans at night, through clouds, with no landmarks, and still return to the same breeding area year after year. Even more shocking, many do it on their first migration. No map, no teacher, just a small brain running navigation like a multi-sensor autopilot. Tonight we break down the real tools: sun, stars, magnetism, sky patterns, smell, landmarks, and the mysteries scientists still can't fully solve. Navigation has two jobs: keep a direction for long distances, and then find a specific destination. A compass can keep you pointed the right way, but it won't tell you where you are. A map can tell location, but only if your brain can turn signals into coordinates. Birds seem to do both, switching modes as the journey changes. Over open ocean, a bird can't follow rivers, roads, or mountains, only wind, waves, and sky. Yet routes remain consistent across years. That suggests birds rely on global cues that don't require landmarks, then use local cues only near the endpoint. It's like flying with instruments first, then visual landing guidance. Bird migration looks impossible because it's not one sense. It's a stack: sun compass, star compass, magnetic compass, and local mapping cues. When clouds hide the sun, stars and magnetism can carry direction. When the sky is clear again, birds recalibrate. The secret is redundancy. Using the sun sounds simple, until you remember the sun moves. To keep a correct heading, a bird must combine sun position with an internal clock. If the clock shifts, the bird's direction shifts. That means timekeeping isn't just biology, it's navigation hardware. Dawn and dusk are special because the sky provides stable orientation cues at low angles of light. Many birds show pre-departure restlessness and alignment behaviors around these times. They're not just getting excited, they're calibrating their compass systems before committing to the long flight. Night migrants can orient using the star sky, but not by memorizing a single star. It's the rotating pattern and the stable center of rotation that matters. Young birds must learn this pattern early, then use it as a nighttime compass. The mystery isn't that they see stars, it's how quickly the brain turns star geometry into north. Magnetism gives birds a compass that works when visibility fails. They can still orient in darkness or heavy clouds because Earth's magnetic field is always present. The open question is the neural display. How does the brain translate a field into a usable direction without conscious effort? One leading idea suggests magnetic sensing may be tied to light-sensitive chemistry, meaning the compass could depend on certain wavelengths. If that's true, the magnetic sense might be integrated with vision, like a faint directional pattern embedded in perception. Scientists can test behavior, but we still don't know what the bird actually experiences. Another hypothesis proposes magnetism could be detected by specialized receptors rather than a visual overlay. If so, it would work more like a built-in sensor sending directional signals to the brain. The controversy is which structures do what, and whether different species use different magnetic solutions. Migration may be one outcome with multiple biological designs. Even when the sun is hidden, the sky contains polarization patterns that provide directional information. Birds can use this as a compass reference and a calibration tool, especially at sunrise and sunset. It's a hidden layer of the atmosphere most humans never notice, but for migrants it can be a reliable guide. Some evidence suggests certain birds can use smell not just for finding food, but for navigation, building a map from regional odor patterns shaped by winds and landscapes. It sounds impossible until you treat the air like a moving chemical geography. The mystery is learning. How does a brain store an odor, map, and convert it into a flight decision? Near coasts, rivers, mountain corridors, and familiar terrain, birds can use visual landmarks to fine-tune their route. This is where navigation looks normal, but the real skill is switching systems smoothly. Instrument navigation across featureless space, then landmark guidance near the destination. That transition is a major part of the magic, without any magic. Migration is also decision-making, choosing altitude, timing, and weather windows to save energy. Birds ride tailwinds, avoid headwinds, and sometimes detour around storms. A straight line isn't always the safest line. What looks like instinct often behaves like strategy. Many migrants rely on stopover sites to refuel and rest. That means navigation includes memory. Where to land, when to leave, and how to continue. Disrupt the stopover chain, and the whole system breaks. Migration isn't just a flight, it's a network. Juveniles often migrate without parents, implying an inherited program. When to go and which general direction. But they still correct for wind and geography, meaning the program must be flexible. This is one of the biggest mysteries. How can a built-in route remain adaptive in a chaotic world? Artificial light at night can confuse celestial cues, and urban environments can distort natural orientation signals. Magnetic noise and habitat fragmentation can also disrupt the map layer. The terrifying truth is that the navigation system works beautifully, but it's vulnerable to human-made changes. Bird navigation isn't supernatural, it's stacked instruments, time, sky, magnetism, atmosphere, chemistry, landmarks, and weather strategy, integrated into one decision engine. The impossible part is not a single sense, but the fusion. Comment the tool that shocked you most, and subscribe to World of Mysteries for the next investigation.